This is the first video in a chapter on chemical bonding and molecular geometry. We have just finished talking about electrons and where they live and how they circle an atom. And now we're going to talk about how atoms use them for bonding, starting with ionic bonding first. So in the last chapter, we talked about orbital diagrams and electron configurations. Those were things that we used to describe electron filling and where electrons live around an atom. So we used orbital diagrams and electron configurations to indicate where each electron is located in an atom. And so now we're going to move on to bonding. Now we will use that information to understand how electrons are shared and transferred during bonding. And you'll find out that some bonding is more like sharing, and some bonding is definitely not like sharing. And those are important features to know about a particular molecule to help us predict its chemical properties. So it's finally time to talk about bonding and compounds with more than one atom in them. So I've cheated and gone ahead and drawn the periodic table ahead of time. So go ahead and take a moment to draw it if you need it. So when we need to look at ionic bonding occurs between ions, and ions have a particular charge. So we need to know what the charge of each ion is to be able to understand how the bonding works. And it turns out the periodic table is, again, a very useful tool for predicting the most likely charge on an atom. So you'll remember last time, a couple of videos ago, we talked about the metals and the nonmetals and the metalloids. So we're going to go ahead and color those in again, because they're going to be important. So the metals are found on the bottom and left part of the periodic table. And the nonmetals are mostly found on the top and right side. And it turns out that whether something is a metal on the bottom left or a nonmetal on the top right is really relevant to predicting the charge on whether something becomes a cation with a positive charge or an anion with a negative charge. So the metals are on the bottom and left, nonmetals at the top and right. So we'll start with metals, because I'm an inorganic chemist and I like metals the best. So metals over here on the bottom and the left side, they prefer to form cations. And cations are positively charged ions that are formed when electrons are lost. And we'll soon talk about how that's because it's easier to lose electrons from metals because they have so few valence electrons. The only exception to this rule is hydrogen, which lives over here in the top box. Hydrogen isn't really like a metal, it's actually a nonmetal, and it's pretty flexible. Hydrogen can form a cation or an anion. So don't worry about hydrogen too much right now. So we can predict what the charge of a particular metal cation might be based on its position in the table, specifically which column or group it lives in. So let's start with the metals on the very left side of the table, over here in groups 1 and 2. It's pretty simple to predict what the charge of those will be. The positive charge should be equal to the group number. For example, if we look at calcium, on a real periodic table. Here's calcium. Over here, it's in group 2. So the most common charge of a calcium ion is 2+, because it's in group 2. So far, so good. We also need a rule for the groups way over on the P block side, groups 13 through 17. I've labeled some of them. I ran out of space to draw all of the numbers, but you can imagine that there are other numbers in here. So for those guys, because their group numbers are so large, when we predict the charge, we can't just take the number straight away, because we know something wouldn't reasonably have a charge of +13. That's just too large to be realistic. We take the group number -10 to predict that charge. For example, we could look at aluminum. Here's aluminum. Over here at the left side of the P block, it is in the first column of the P block, which is group 13. So the most common charge for aluminum is going to be 3+. From group 13 -10. And it makes sense as you go along. You'll get it. And of course, you've noticed that I've conveniently skipped the transition metal block, the D block in the middle. And that's because there's not as safe a way to make a good prediction for these cases. These metals are particularly good at becoming cations, but they can become all different kinds of cations with different kinds of charges. And so for a metal, a good guess would be to guess that the metal has a 2+ charge or a 3+ charge, losing those electrons from its highest shell s orbital. But it's much more difficult to predict these, so we won't worry too much about that right now. So groups 1 and 2, just take the group number. Groups 13 through 17 over here in the P block, group number -10. All right, now let's do the nonmetals. So as you might have guessed, the metals like to form the cations, and so the nonmetals prefer to form anions. So they prefer to gain extra electrons, giving them a negative charge. And when we talk about nonmetals gaining a negative charge, we are specifically excluding group 18, the noble gases. Noble gases do not form ions. So we're not really talking about them. They don't like to form ions at all. There's only one rule for this side, because all the metals are in the P block. All the nonmetals are in the P block. And to find the charge for these groups, we are going to take the group number -18, because we're anticipating getting a negative charge. So if we look at oxygen, for example, oxygen over here in the 4th row of the P block, it's in group 16. So the most common charge for oxygen would be 2-, which is group 16 -18. And you're probably starting to see the pattern that's happening here as we give these sort of arbitrary rules for predicting. You can see that the number of electrons gained or lost is related to that electron configuration that we toiled over in the last chapter. It's all starting to come together. So we can see that each of these different atoms, whether they're metals or nonmetals, they gain or lose their valence electrons, those ones that are on the outermost shell, in order to try to match the electron configuration of the nearest noble gas. And that kind of fits in with what we said earlier, right? We said that noble gases don't form ions. They have the perfect number of electrons and they're very happy just to exist on their own. Thank you very much. And so all of the other atoms are looking to reach that same level of stability. And while they can't change their number of protons to actually become a noble gas, they can change their number of electrons to reach that same electron configuration. So let's look back at some of those examples we showed. So we looked at the element aluminum. So if we wanted to write the electron configuration of aluminum, which is right here, we can write the shorthand version, which starts with the previous noble gas. So the previous noble gas was neon. And then we fill in the electrons going forward. So the next block is the 3s orbital, and that one is filled. And then aluminum lives in the 3p orbital, which has 1 electron in it. So 3s2, 3p1. And so aluminum can either lose electrons to have the same configuration as neon, which would involve losing 3, or it could gain 5 electrons to have the same configuration as argon. And so 3 is less than 5, and 3 electron transactions are easier to do than 5 electron transactions. So that's why aluminum prefers to go to aluminum 3+, because by losing 3 electrons, it has the same configuration as the noble gas neon. It looks similar for oxygen. So oxygen lives here in the second row. So the last noble gas before oxygen was helium. So we can start its shorthand configuration with helium. Then after helium comes the 2s subshell, which is filled, and the 2p subshell, which has 1, 2, 3, 4 electrons in it. So we've got 2s2, 2p4. And if we want to get the oxygen close to a noble gas configuration, we can either subtract 1, 2, 3, 4, 5, 6 electrons to have the same configuration as helium, or we can add 1, 2 to get the same configuration as neon. So adding 2 is easier than subtracting 4. So that's why we often see oxygen 2+ with the same configuration as the noble gas neon. All of these electron transactions are really expensive, and each atom wants to minimize the number of electron transactions it takes to get to a noble gas configuration. And so some of them end up being cations, and some of them end up being anions, depending on which direction has the fewest number of transactions. So in the next video, we will talk about a special kind of ion called a polyatomic ion.